Hello and welcome to this video. My name is Victor Weiss from TU Wien, and I'm happy to share with you our recent publication, Gas Phase Electrophoresis on nES GEMMA instrumentation of SARS-CoV-2-Based Virus-like Particles. Our manuscript was published in ACS Omega, and on this slide you can see the corresponding abstract, as well as the QR code which will direct you to our publication. With this video, I want to present you the aim of our work. I want to go into detail concerning gas phase electrophoresis, in case you are not familiar with my other videos on YouTube. I want to present you some of our results, and at the end I want to give you a short conclusion and maybe outlook to some future projects. So what about the aim of our work? Over the recent years, we have analyzed quite a number of different viruses and virus-like particles with gas phase electrophoresis on a nES GEMMA instrumentation. With the current manuscript, we asked ourselves if SARS-CoV-2-based virus-like particles can be analyzed via gas phase electrophoresis on a nES GEMMA instrumentation as well. But what is actually nES GEMMA? nES GEMMA is short for Nano-Electrospray Gas Phase Electrophoretic Mobility Molecular Analysis, or analyzer. The same instrument is also known under several other names, for instance macro-IMS, LiquidScan-ES, ES-DMA, or ES-SMPS, which makes literature research a bit complicated. All those instruments are, however, doing the same thing. They are separating single-charged analytes in the gas phase at ambient pressure according to the so-called electrophoretic mobility, or EM diameter, which is the particle diameter in case of spherical analytes. Our instrument consists of three parts. First, we have the so-called nano-electrospray aerosol generator with a charge reduction device. More to that in a minute. Secondly, we have the electrostatic classifier with a nano-differential mobility analyzer. So that's the part where the magic occurs. And that's that cylinder which you can see here on the right-hand side of the instrument. And last but not least, we have the so-called condensation particle counter as detector unit of our instrument. In the first part of our instrument, in the nano-electrospray source, we have to transfer our analytes from the liquid to the gas phase. We are doing that via a classical electrospray process, which means we are dissolving our analytes in a volatile electrolyte solution, typically ammonium acetate, and then we're applying pressure, an electric field, as well as a sheath flow at the tip of a cone-tipped capillary in order to generate droplets. We are drying down those droplets, and at the same time, charge equilibration occurs in a bipolar atmosphere induced, for instance, by a 210 polonium alpha particle source, a soft X-ray charger, or a corona discharge process. In the end, we obtain mostly singly charged analytes, which we are then introducing to the second part of our instrument, the nano-differential mobility analyzer. Here, two forces are acting on our analytes. First, a tunable electric field, and in a perpendicular direction, a high laminar sheath flow of particle-free filtered ambient air. By variation of the field strength, it's then possible to size separate our analytes from the polydisperse aerosol, and what we get in the end is monodisperse aerosol fractions, or actually monomobile aerosol fractions. These we are then introducing to our condensation particle counter, where we have a supersaturated atmosphere of, for instance, N-butanol or water. Our aerosol particles act as condensation nuclei, and we are forming droplets which we then can count as they pass a focused laser beam. What we get in the end is a spectrum, as you can see here, for an exemplary protein. On the x-axis, we are displaying the so-called EM diameter, and on the y-axis, particle count values. So what we get in the end is really surface dry particle diameters with number-based particle detection in good accordance with the recommendation of the European Commission for nanoparticle characterization. But let's have a closer look maybe on the nano-differential mobility analyzer. Just to remember, that's the part where the magic occurs for separation, where we have a tunable electric field and in perpendicular direction a high laminar sheath flow of particle-free filtered ambient air. What we can do in the nano DMA is we can vary the sheath flow values. When doing so, when reducing the sheath flow, we are gaining actually measuring range, which means we are also able to detect larger nanoparticle material. At the same time, also the peak width of our peaks is increasing, which leads in the end to a reduced resolution between peaks. This was something which we checked with our recent publication. We analyzed SARS-CoV-2 VLP containing samples, applying several different sheath flow levels in the nano differential mobility analyzer. At 3.5 liters per minute, as you can see here on top, we are obtaining signals up to approximately 150 nanometers EM diameter. At the same time, we have rather broad peaks with not so good resolution between those. In contrast, at 50 liters per minute, the sizing range is reduced to values up to approximately 64 nanometers, and at the same time, the peak width is significantly improved and we are gaining resolution between peaks. Of course, we also checked values in between those two maxima, and you can find those results in our publication. The other thing which is of importance is that there are several ways how to plot your results. As you can see here on that slide, it's possible to plot particle count values, and on the other side, it's also possible to have number-based or actually mass-based particle detection. What does it mean? Going back to the scheme of our nES GEMMA instrumentation, just remember that we have our nano differential mobility analyzer, where we are separating our analytes in a tunable electric field and a high laminar sheath flow. And then we are detecting our particles in the CPC unit. Usually, when we are just relating count events in the CPC to applied voltage values, we are obtaining so-called raw data values. In the next step, it's possible to calculate, based on applied voltages, actual EM diameter values and to relate those to counting events in the CPC. What we then get are so-called particle or raw counts. And then there is the possibility to further improve or to further process those values, for instance, via mathematical corrections for detector efficiency or multiple charge correction, and so on and so forth. When doing so, we are getting, for instance, number or mass-based data. The differences between particle count values as well as mass-based data evaluation you can see here on that slide. On the left-hand side, it's particle counts. On the right-hand side, it's mass-based data evaluation. So depending on the instrument settings, different information can be gathered on analytes. We then subsequently checked, of course, SARS-CoV-2 VLP containing samples with our setup. In order to be able to do so, what we had to do is we had to desalt our VLPs first and to remove non-volatile buffer components of the storage buffer. We applied spin filters with 10 kilodalton molecular weight cutoff, and of course checked the outcome of our desalting process via NTA measurements. As you can see here, the results which we are also presenting in our manuscript show that desalting worked. We obtained particles in the corresponding size value as found with NTA. We also checked the presence of antigenic material inside our samples via a classic antigen test. And the line at the T is a sign that we still have some infectious or not infectious, but material which is recognized by antibodies inside our sample. And last but not least, of course, we took our samples then to gas phase electrophoresis on our nES GEMMA instrumentation. And on plot C and plot D, you can see results for particle count evaluation as well as for mass-based data evaluation. Especially for D, so for mass-based data evaluation, it's nice to see that we have some particles there in the sizing range between 50 and approximately 150 nanometers EM diameter. Those particles correspond to SARS-CoV-2 virus-like particles. Of course, we also checked our samples with higher sheath flow levels and concentrated on the lower EM diameter sizing range. When doing so, it was possible to fit several Gaussian shaped peaks to our signals. At the same time, we also checked VLP decomposition via heating and found that this is something which you can see in plot C, that we had some unspecific aggregation inside our samples. At the same time, particle count values in overall declined as found via NTA analysis, as well as the line at T when doing a second antigen test was significantly diminished. Taking now peak values or peak EMD values as displayed in plot A to EM diameter molecular weight correlation enabled us to also calculate molecular weight values of those peaks based on gas phase electrophoresis data. A corresponding manuscript you can find when you follow that QR code. Especially one of those peaks, peak number 9 with an EM diameter of approximately 9.5 nanometers, might correspond to SARS-CoV-2 protein. To conclude, with our current manuscript, it was possible for us to demonstrate that SARS-CoV-2 can be analyzed via gas phase electrophoresis on an nES GEMMA instrumentation. We obtained quite a broad peak, with results comparable to NTA data. We were able to detect low molecular weight material next to intact VLPs. We could show that sample heat denaturation leads to unspecific aggregation. And of course, what we want to do next is we want to focus on other SARS-CoV-2 VLP variants as well as other VLPs as well. Thank you very much for your attention and see you with our next video. Bye.